Lesson 27, the nucleus. Part 1, elements and isotopes. The atom is made up of three kinds of subatomic particles. The proton has a mass of 1.6726 times 10 to the negative 27 kilograms. And it has a charge of positive 1.6 times 10 to the minus 19 coulombs. The neutron is slightly heavier than the proton. It has a mass of 1.6749 times 10 to the minus 27 kilograms, and a charge of 0 coulombs because it's a neutral particle, hence the name the neutron. The electron is the smallest of the subatomic particles, with a mass of 9.1094 times 10 to the minus 31 kilograms, and a charge the same as a proton, 1.6 times 10 to the minus 19 coulombs, except negative. Protons and neutrons are both found in the nucleus of the atom. For this reason, protons and neutrons are both referred to as nucleons. Nucleons are the particles found in the nucleus. Electrons, on the other hand, are found outside the nucleus. Electrons are found in the energy levels surrounding the nucleus. They can jump up and down through the energy levels, absorbing and emitting photons. Protons and neutrons are important parts of the nucleus. The number of protons in the nucleus determines the element. For example, gold has 79 protons. Gold is yellowish and solid metal. Mercury has only one more proton. Mercury has 80 protons, and mercury is a silver liquid metal. Just changing the nucleus by one proton completely changes the property of the substance. Isotopes are atoms of the same element with different numbers of neutrons. For example, carbon-12 has 6 protons and 6 neutrons, while carbon-14 has 6 protons and 8 neutrons. The protons don't change, so it's still carbon, but the neutrons change, which means that we have a new isotope of carbon. Isotope notation is the way we write the symbols for different isotopes of the same element. The symbol for an isotope is written in the form XAZ, where X represents the element symbol. Z is the atomic number. This is the number of protons found in the nucleus. And A is the total number of nucleons. Nucleons are the protons plus the neutrons. You'll notice that nowhere in the isotope notation is the number of neutrons listed. To find the number of neutrons, you subtract the atomic number from the number of nucleons. Here's an example. One isotope of uranium is uranium-235. This has the symbol U for uranium. The number of protons found in uranium is the atomic number, 92. The number of nucleons in uranium-235 is 235. Because it's uranium, the atomic number cannot change. There are 92 protons found in uranium-235. The number of neutrons can be calculated. It's 235, the number of nucleons, minus 92, which is the number of protons. This gives us 143 neutrons. Uranium-235 has 143 neutrons. There's another isotope of uranium, uranium-238. This has the symbol U. Still 92 because the atomic number for uranium cannot change. But the number of nucleons in uranium-238 is 238. So we still have 92 protons. But now we have 238 minus 92 neutrons, which is 146 neutrons. We're going to be working with several different alternative units for mass as we study particle and atomic physics. This is just like how in Canada we use meters and in the States they use inches and feet. They're just alternative units to measure the same thing. The atomic mass unit is an alternative unit of mass used for very small particles. The atomic mass unit is, by definition, the average mass of a nucleon in the carbon-12 isotope. The mass of the carbon-12 isotope, which is an isotope of carbon with 6 protons and 6 neutrons, is 1.992648 times 10 to the negative 26 kilograms. One atomic mass unit is this mass divided by 12. 1.992648 times 10 to the negative 26 kilograms divided by 12. This gives us one atomic mass unit equals 1.66054 times 10 to the negative 27 kilograms. On your formula sheet, one atomic mass unit is given as 1.66 times 10 to the minus 27 kilograms. This is the precision we will use for future lessons, but for the purpose of this lesson, we will use the more precise value of one atomic mass unit to help you understand more about nuclear binding energy and how it works. Look for the lower precision version in future lessons. Example: convert the mass of the proton, neutron, and electron into atomic mass units. We'll start with the proton. The mass of the proton in kilograms is 1.6726 times 10 to the negative 27 kilograms. To convert this into atomic mass units, we divide by 1.66054 times 10 to the negative 27 kilograms per atomic mass unit. This allows us to cancel out the kilogram and leaves us with atomic mass units. This gives us 1.007276 atomic mass units for the proton. The neutron is 1.6749 times 10 to the negative 27 kilograms. This is equivalent to 1.008664 atomic mass units. The electron is much lighter and smaller. The electron is 9.1094 times 10 to the negative 31 kilograms, which is equivalent to 0.000548 atomic mass units. In Physics 30, for your diploma exam, you will be given a periodic table. This periodic table has less information on it than the standard chemistry periodic table, but it has some important details. Here's a square on the Physics 30 periodic table. It tells you the element's symbol and name. This is Fe, the symbol for iron. The atomic number for the element. This is the number of protons found in the nucleus. You might have heard of this as the atomic mass, or in some cases, the number of grams per mole for the element. In physics, the atomic mass is the average mass of the nucleus in atomic mass units. The masses given on a periodic table were found using a mass spectrometer. A simple mass spectrometer consists of a velocity selector, which selects ions of a particular velocity, so the velocity is known, and an ion separator region, which allows the particles at a velocity to travel with a circular path. In the velocity selector, there is a perpendicular magnetic and electric field. In the velocity selector, shown in the picture above, the electric force is equal to Q, the charge of the ion, times the electric field strength. In this example, the direction of the magnetic force for a negative ion is up, opposite to the direction of the magnetic field. The magnetic force is QVB, and for a negative charge, this magnetic force would be down. We can find the direction of this force using our hand rule. For a negative charge, we point the thumb of our left hand in the direction of the particle's velocity, we point our fingers in the direction of the magnetic field, and our palm points down to show the direction of the force. When the electric and the magnetic forces are balanced, Fe equals Fm, and QE equals QVB. In this case, Q appears on either side of this equation, so Q can be cancelled out. This gives us the velocity in the velocity selector equals the electric field divided by the magnetic field. Second stage of mass spectrometry is the ion separator region. In the ion separator region, there is a magnetic field only, and as a result, the particles travel in a circular path. In this case, the magnetic force is equal to the centripetal force, so QVB is equal to mv squared over r. Since v appears on both sides of the equation, v can cancel out from each side once. We can rearrange this for m. M equals q b r divided by the velocity. Here's an example. A singly charged ion passes through the velocity selector of a mass spectrometer undeflected. Singly charged means it's 1 times the elementary charge. Then they enter the separation region and are deflected with a radius of 8.12 meters. What is the mass in atomic mass units? We'll start by determining the velocity given by the velocity selector. The velocity of a particle that's undeflected through the velocity selector is equal to the electric field strength divided by the magnetic field strength. This is 7,000 volts per meter divided by 0.25 teslas. This gives us a velocity equal to 28,000 meters per second. After the velocity selector, the particles enter the mass spectrometer region. The mass for a particle traveling with circular motion through a magnetic field is given by Q, B, R over V. Since it's singly charged, this is 1.6 times 10 to the negative 19 coulombs times the magnetic field of 0.25 teslas times the radius of 8.12 meters divided by the velocity, which is 28,000 meters per second. This gives us a mass in kilograms equal to 1.16 times 10 to the negative 26 kilograms. Next, we need to change this to atomic mass units. We have a mass equal to 1.16 times 10 to the negative 26 kilograms. We divide this by the atomic mass unit, which is 1.66054 times 10 to the negative 27 kilograms per atomic mass unit. The kilogram cancels out and leaves us just with atomic mass units. So this is a mass equal to 7 atomic mass units. Part 2. Mass defect and nuclear binding energy. The mass of each isotope for each element has been measured precisely using a mass spectrometer. But when scientists predict what the mass of each isotope should be based on the number of protons and neutrons found in the nucleus, they find a discrepancy between the predicted amount and the actual measured value. For example, if you look at the deuterium isotope of hydrogen, the measured mass of deuterium is 2.014102. But if you look at the components of the hydrogen nucleus, for deuterium you have 1 proton, 1 neutron, and 1 electron, and you add the mass of each of these together, you get 2.016490. There's a discrepancy between these two masses, and this discrepancy is called the mass defect. We're going to look at some isotopes of oxygen for some examples. Oxygen 16, oxygen 17, and oxygen 18. Oxygen 16 is O 16, 8. Oxygen 17 is O, 17, 8. And oxygen 18 is O, 18, 8. In each case, the oxygen isotope has 8 protons. But each oxygen isotope has 1 more neutron. Oxygen 16 has 8 neutrons, oxygen 17 has 9 neutrons, and oxygen 18 has 10 neutrons. You can predict what the mass of each nucleus of the isotope should be based on its components. Oxygen 16 is made up of 8 protons and 8 neutrons. This is 8 times the mass of a proton, which is 1.007276 atomic mass units, plus 8 times the mass of a neutron, which is 1.008664 atomic mass units. This gives us a predicted mass equal to 16.127392 atomic mass units. You can do the same for each isotope of oxygen. For oxygen 17, it's 8 protons plus 9 neutrons. And this gives us a predicted mass of 17.136056 atomic mass units. And for oxygen 18, it's 8 protons plus 10 neutrons, which is a predicted mass of 18.14472 atomic mass units. But when the mass of each isotope is measured, we find a discrepancy. While the predicted mass for oxygen 16 is 16.127392, the actual mass is 15.99491463. In each case, when you compare the predicted mass to the actual mass, we find that there is some small amount of missing mass. This missing mass is referred to as the mass defect. It's the difference between the predicted mass and the measured mass of an isotope. We write this as delta M, or change in mass, and this is the theoretical mass, or the predicted mass, minus the measured mass for an isotope. Where did the mass go? When a nucleus forms, a certain amount of energy is needed to hold all the nucleons together. Separately, they have a greater mass. When you combine them together, they have a smaller mass. Some of the mass is converted to the nuclear binding energy to hold the nucleus together. Einstein showed that mass and energy are interchangeable. Mass and energy are equivalent in the formula E equals mc squared. In this formula, E is energy, always measured in joules. M is mass, measured in kilograms. And C is the speed of light. This is 3 times 10 to the 8 meters per second. For oxygen 16, the nuclear binding energy can be calculated. The mass defect for oxygen 16 is the theoretical mass minus the measured mass. For oxygen 16, this is 16.127392 minus 15.99491463. This mass defect is equal to 0.13247737 atomic mass units. To calculate energy from mass using Einstein's equation, we need to convert this mass into kilograms. So we multiply by 1.66054 times 10 to the negative 27 kilograms per atomic mass unit. Atomic mass units cancels out and leaves us with kilograms. This gives us a delta M equal to 2.1998397 times 10 to the negative 28 kilograms. It seems like a really small amount of mass, but remember the electron is 9.11 times 10 to the negative 31 kilograms, which is significantly lighter than the missing mass. Next, we use Einstein's equation, E equals mc squared, to find the mass defect in terms of energy. This is 2.1998397 times 10 to the negative 28 kilograms times the speed of light squared, which is 3 times 10 to the 8 squared. This gives us an energy equal to 1.979856 times 10 to the negative 11 joules. Scientists won't often leave their energy in this small amount of joules. They want to convert it into electron volts. To convert into an electron volt, we divide by 1.6 times 10 to the negative 19 joules per electron volt. When you do this, joules cancels out, and we're left with electron volts. This gives us an energy equal to 123740984 electron volts. This number is a little bit awkward too because it's quite large. To fix this, we convert into mega electron volts. Mega is 10 to the 6. To do this, we divide by 1 times 10 to the 6. This gives us energy equal to 124 mega electron volts. Let's review these units of energy. To convert joules to electron volts, we divide by 1.6 times 10 to the negative 19 joules per electron volt. To convert electron volts to mega electron volts, we divide electron volts by 1 times 10 to the 6 to get mega electron volts. What is the nuclear binding energy for the helium-4 nucleus if the measured mass of helium is 4.00150 atomic mass units? Helium-4 is helium with 4 nucleons and 2 protons. This means we have 2 protons and 2 neutrons in the nucleus. To find the theoretical mass, we add the mass of 2 protons, which is 2 times 1.007276, plus the mass of 2 neutrons, which is 2 times 1.008664. This gives us a theoretical mass equal to 4.031882 atomic mass units. The mass defect is the theoretical mass minus the measured mass. This is 4.031882 minus 4.00150. This gives us a mass defect equal to 0.030382 atomic mass units. When we convert this into kilograms, we get 5.045053 times 10 to the negative 29 kilograms. Applying Einstein's formula to this mass, we get E equals mc squared equals 5.045053 times 10 to the negative 29 times c squared, which is 3 times 10 to the 8 squared, giving us a very small amount of energy equal to 4.54 times 10 to the negative 12 joules. We can convert this to electron volts and we get 28375,000 electron volts, which is 28.4 mega electron volts. So the nuclear binding energy for the helium-4 nucleus is 28.4 mega electron volts. So far you've learned a couple units for mass, which are the kilogram and the atomic mass unit. There's a third alternative unit of mass, the mega electron volt per c squared. The mega electron volt per c squared is another alternative unit of mass used in nuclear and particle physics. This unit tells us the amount of mega electron volts that would be released if the entire mass of the particle were converted into energy. We'll use the lithium-7 nucleus for an example. The mass of the lithium-7 nucleus is 7.016004 atomic mass units. What is the mass of lithium-7 in mega electron volts per c squared? First, we need to convert this mass of 7.016004 atomic mass units into kilograms. To do this, we multiply by 1.66054 times 10 to the negative 27 kilograms per atomic mass unit. This gives us a mass equal to 1.16504 times 10 to the negative 27 kilograms. Next, we use Einstein's equation to convert to joules per c squared. If we multiply the mass of the lithium nucleus, 1.16504 times 10 to the negative 27 kilograms, by c squared over c squared, which is essentially just multiplying by 1, and only one of this c squareds is turned into a number, 3 times 10 to the 8, and then squared, the other c squared is left there to make the unit look pretty, we get 1.048532 times 10 to the minus 9 joules per c squared. Next, we convert these joules into electron volts to get electron volts per c squared. 1.048532 times 10 to the negative 9 joules per c squared divided by 1.6 times 10 to the negative 19 joules per electron volt gives us 655.3324846 electron volts per c squared. Our final step is to convert these electron volts into mega electron volts. Mega is 10 to the 6, so we just divide by 1 times 10 to the 6 to turn it into mega electron volts. And we get a mass equal to 6,553 mega electron volts per c squared. To recap, we have two units of mass that are alternatives to the kilogram, the atomic mass unit and the mega electron volt per c squared. To convert kilograms to atomic mass units, we take our value in kilograms and we divide by 1.66 times 10 to the negative 27 kilograms per atomic mass units to get our number in atomic mass units. Converting from kilograms to mega electron volts per c squared is a little more tricky. We take our value in kilograms and we multiply it by c squared over c squared. Only the top c squared ends up actually being used as a number, and this gives us some value in joules per c squared. Next, we take our joules per c squared and we turn into electron volts per c squared. To do this, we divide by 1.6 times 10 to the negative 19 joules per electron volt to get our answer in electron volts per c squared. Finally, we turn our electron volts per c squared into mega electron volts per c squared. To do this, we take our electron volts per c squared and we divide by 1 times 10 to the 6 electron volts for each mega electron volt. This gives us our answer in mega electron volts per c squared.